Okay, we're going to continue our discussion of how to do these drawings with roof monitors supported by trusses. And you might want to actually just start drawing in this file I'm giving you because there could be some things that I've drawn in there that you just want to borrow and insert into your drawing. Um, but I'll leave that up to you. You should probably start though by making sure you have established the key features of the new geometry. And one of the things you can't do is you can't just take the entire drawing and scale it because different parts of it um, would scale differently. So, but it could be useful to you to just draw in that same file. So I'm going to go there and while I'm here, I'm going to make another point that I forgot to make earlier. I've done some projects like this, and one of the things that turns out is you can do this whole window framing system here, glazing system, as some kind of variant of a curtain wall or as what we call storefront. And both those systems have a bunch of vertical mullions that are used to join the pieces of glass along the vertical connections or the so-called head joints in the glass. So you have mullions top and bottom and then a bunch of vertical mullions. Systems like that tend to be pretty expensive. And so one of the things I've learned is the following. This dimension for the glass is rarely so large that we can't just span from this lower support edge to the upper support edge without any structural need for vertical mullions. So we can save an enormous amount on the assembly costs and also on all the mullion cost if we just basically have a troffer down at the bottom, like what I've drawn here, and a troffer at the top. And that is the means of making the structural connection between the glass and the structural frame, which has to support the glass against wind overpressure and wind suction and so forth. So you'll notice, by the way, in this troffer down at the bottom, I didn't make it as deep as the one at the top because gravity is going to cause the glass to stay down in this 3/4 inch deep troffer. On the other hand, near the top, uh, the structure deflects some under loads, which can be variable, like live loads of people walking across the roof or drifting snow loads that produce unexpected deflections. Um, to keep the glass from falling out or alternately being crushed, we have to provide an airspace above it. So I put an half-inch airspace up there between the neoprene gasket and the top of the insulated glass panel. So that is our structure, our way of waterproofing and holding the glass in. Now, the horizontal glass will run for a certain number of feet, which in our case probably is from one vertical um, web member to the next. And I just say that because we're probably going to put in a silicone head joint between the two pieces of glass that meet there. And while that silicone head joint is not visually terribly obtrusive, it can be it will be visually apparent. And if we kind of put it in front of a vertical mullion, a vertical web member rather, it's less likely to be noticed. So we're lining up that joint, that head joint in the glass with the vertical web member. Um, so and the joint between them won't be a mullion, it will be just a silicone head joint. All right, so having said all that now, I'm going to start trying to set up our 100-foot long version. And I'm going to put in a line here. And I'm going to start drawing that line. And I know that 100 feet is 1,200 inches, and my basic units in AutoCAD are inches. So there is a line that represents the center, the joint to joint dimension, which was literally from right there in this to right there. So keep in mind, there'll probably be a column under this end and a column under that end, and we typically put the columns on a nice clean grid, like 100 feet. And that means we'd like for this end web member, which is carrying all the load of this truss, to be aligned with the column down below. Everything that structural engineers do works off the center lines of these members. Now, typically architects want a different kind of dimension. They want to know the dimension from the top of the top chord to the bottom of the bottom chord. And in fact, for standard trusses, that's the way they're typically sold. So the architect will specify the depth of the truss. The engineer will look at all the other situational issues and figure out where the centroids of um, the top and bottom chords are based on some initial estimates of the size of those members. And the engineer will then do all that analysis and come back and decide whether the original member dimensions were adequate. Um, if they are, then the architect doesn't have to redo this drawing. But the key point is to remember that architects want to work off of attachment surfaces like the top of the top chord and so forth. But the engineer sooner or later has to get down to the centroids. And so we're going to start drawing this whole thing from the centroids. So I'm going to say that's the centroid of the top chord, or maybe for the moment I'll make it the bottom chord. And I'll typically come and I'll find a line type. And in this case, I want to do a center line. And there's one. And sometimes to make these less apparent, I will turn them green or some color. And it also helps me play those down in the drawing and avoid confusion. But for the moment, I'm going to just leave that the way it is. So in the example I'm working, we've said that this member is going to be 4 inches deep. And so I'm going to do an offset here, and I'm going to say I want 2 inches, and I'm going to offset that in that direction and offset it in that direction. Now that's the top and bottom of those chord members. And now I don't want the dashed lines anymore. So I'm going to go back and pick a continuous line, and that defines my member. So now I have said in the past, for simplicity of this whole drawing process, we're going to put a 1/2 inch ceiling down below. So I'm going to do an offset of 0.5. And by the way, in AutoCAD, you do an offset by typing the letter O and hit return. And then you put in whatever you want that offset to be. So in this case, I made it a 1/2 inch. So that 1/2 inch gap right there represents the sheetrock ceiling, or it's a it's a placeholder just for the moment to remind us that there is a surface there. Okay, so now another interesting thing was that we said we wanted at least 6 inches for airflow at the end. So I'm going to come here and I'm going to draw a line, a vertical line, and I'm going to go up 6 inches. And then I know that my sloped roof, the bottom of the corrugations are going to be at that point right there. Now, I also said that I worked out the numbers, and oh, let me do the following. I have provided for you online, and I may update the numbers a little bit, but this is a glass dimensioning tool. And so we're looking at 2 roof monitors per bay, and we've said the bay is 50 feet. And as I said, you could go do this with 1 roof monitor per bay, and you could make this 25. And then we'd come over here and we'd say, okay, we only have one of those. And then we get the same answer either way. But I'm working with this portion here that says 2 roof monitors per bay. So that tells me that, sorry, I did something wrong here. Let me walk through this and you'll see what I'm talking about. Okay, so the crucial line here is line 16, and I'm saying the length of the bay is 100 feet, where the length is parallel to the apertures. The width of the bay is that perpendicular direction, and it's 50 feet. And then I multiply those two numbers. So you see that in the formula up here. It's A16 times B16 gives me the floor area that I'm trying to illuminate. And then we said the aperture area to floor area ratio is 20%, or in other words, 0.2. And if I multiply that 0.2 times this, the floor area, I'll get the required unobstructed glazing area. So you'll notice this is C16, which is the floor area, times D16, which is the aperture to floor area ratio, which gives me the unobstructed glass area. Now, we're going to use some strange terms here. We often talk about nominal dimension and actual dimension. So, for example, in a 2x4, it shrinks during curing and then it gets planed down. So it was sawn originally at approximately 2 inches by 4 inches, but then it shrinks and then it gets trimmed down. And so its overall dimension is 1.5 by 3.5. We call that a nominal 2x4, but we know it's not 2 inches by 4 inches, it's 1.5 by 3.5. So I have put here that same kind of terminology, the nominal horizontal dimension of one glazing panel. And in this cell, I just set that equal to A10. In other words, I'm saying the glass is running the full horizontal length of the bay. And by the way, it doesn't have to go out that far. You can put in another number here, And the motive that some people have is they think roof monitors and sawtooths are kind of ragged and create sort of an aggressive form on the facade of the building. So they want to set these roof monitors in and make the roof monitors shorter than the full length of the bay. There are a lot of really uh, challenging structural problems and detailing problems to doing that, but it does create a form that some people like better. For our purposes, though, we're just going to make this equal to 100. And then we have this pretty good estimate that the webs and any mullions, we don't have any vertical mullions, but the webs and any vertical mullions tend to obstruct about 10%. And that means that if we want to get to the fraction of the nominal horizontal dimension um, of one glazing panel that's available to admit light, in other words, not obstructed by vertical mullions or web members, we're going to say it's 90% or 0.9. Now, if we multiply that 0.9 times the nominal length, so here you see we're multiplying cell F16 times G16. That's this, the nominal length, times the uh, fraction that's not obstructed. We get effectively 90 feet. Now, we've said we have 2 mullions per 50-foot wide bay, and there are 2 pieces of glass in the mullion. So in other words, we have 4 pieces of glass with an effective length of 90 feet. That means we need 4 times 90 is 360, or we have 360 horizontal linear feet of unobstructed glass. Now, if we go here and we say, this is E16 over J16. So this is the area of glass that we need, unobstructed area. This is the horizontal available. If we divide this horizontal available into 1,000, that gives us the clear vertical dimension of the glazing above any obstructions down below and below the truss top chord, because the truss top chord shouldn't obstruct the glass either. So 2.78 feet, or that turns out to be, let me make sure I did this right. That's 33.33 inches. Okay. All right. That's correct. So you're going to do your problem and you're going to substitute different numbers here, but it's pretty important that you go through this and convince yourself you actually understand what each of these steps in this process is, and then you can safely use this spreadsheet to perform those calculations for you. I'm just checking something one more time. Okay. So remember that 33.33, because we're going to have to do an offset for that to represent the glass. So now I'm going to go back here and I'm going to draw a line. And by the way, for the moment, I'm going to bring this. I'm going to copy that over to there. And now I'm going to go back to this. And you'll recall that we ran this number, 100 feet times a quarter of an inch per foot is 25 inches. So that's how much higher everything is at this end compared to what it is at that end. So when I come back to my drawing, I'm going to take this and I'm going to draw a line. And I'm going to make the length of that 25 inches. And now I know that the sloped bottom surface of the corrugated decking is going to go from there to there. So in this example, we had a 15-foot rise. In this example, we have a 25 inch versus 15 inch. So you can begin to see all of this is scaling up the appropriate amount relative to this shorter bay. Okay, so now I'm going to do my offset function and I'm going to put in 3 inches. And that's my corrugated decking. And then I think we said the insulation is 6 inches. So I'm going to do the offset of 6 inches. And this is, whoops, didn't do that right. That's the 6 inch insulation. Now, when I did those offsets, by the way, they kind of pulled away from the vertical at this end. So the way I'm going to fix that is I'm going to say we're going to extend these two lines until they get to that line. And then we're going to close those off like so. And then we got to go do something like that at the other end. It's up there. We're going to be trimming. And in fact, what we can do is we can say fillet. And we'll take this line and we'll go up and connect to that one. And now we're going to have to trim a little teeny bit right there. In reality, of course, the builder might never make such a delicate cut and will sort of cut it coarsely and manage to make it work one way or another. Okay, so I'm going to come here and I'm going to hit H for hatch. And then I'm going to come and I'm going to match MA. That to that. And that's the symbol I'm using for my insulation. Now, I also did something else on this drawing, which is not a very good drawing, but I'm going to do it this way anyway. I'm going to hit hatch. Uh, this is one of the annoying features of AutoCAD that it occasionally tells me there's not a closed boundary, but there should be. So the nice thing though is they have this new feature where I'm going to just close this. So I hit close and maybe it'll do it. And it's still telling me that something isn't closed. All right, so I'm going to say, all right, I'm going to do this the really hard way. I'm going to take a polyline. I'm going to click right there. And then I want to go way over here. Okay, so that finally worked. And now I'm going to go get this weird looking hatch, which typically, if I'm really serious about towards the end of this drawing process, I'll draw a piece of this that shows in a little detail um, the corrugations. But for right now, I'm just sort of putting these lines in there to represent the vertical web material of the corrugations. And this is what I'm using as a non-standard format, but it kind of works for the preliminary stages of this kind of thing. So now I've got the corrugated decking right here, the sloped insulation right there. All right, now I'm going to say the curb needs to be about 4 inches at the top. So if I'm going to do that, I'll come and put a line here that's 4 inches high. And then I'll come out from there and I'll say that's the top of the curb, which also defines the bottom edge of the glazing, or roughly. So now I'm going to click F and I'm going to fillet these two things. And now actually, if I go with the same detail that I drew below, I'm going to do an offset of 4 inches. And now that's that aluminum extrusion, which is 4 inches deep at the top, and that's forming the curb there. And then we have this additional height for the curb at this end, which is that 25 inches. Okay, so now we said the glass is 33.33 inches above that. So I'm going to do an offset of 33.33 inches. And these lines then define the lower and upper exposed edges of the glass. In other words, this is the vertical dimension of the portion of the glass that can let light through. Now the glass goes down and buries itself a little bit down here, and it buries itself up above. So it's actually going to be an inch and a half bigger than these two lines, but this represents the vertical dimension of the exposed glass. So now we get up to the top here, and we're going to have another mullion-like element, but we're also going to have the top chord, which in my case is 4 inches. So I hit offset and I say 4 and enter. And depending upon where I'm taking my section cut, um, this will either be um, the upper mullion or troffer, as I refer to it, um, or it will be the so I showed this section here, so we'd actually be looking at um, that upper mullion. But for the moment, I want to focus now on the trusses because I want to size some trusses and um, see where we stand. So I'm going to come here and I'm going to say, let's do an offset of 2 inches. And that becomes the center line of the top chord. And then I'm going to do MA for match and make that a center line. And now I'm going to come along here and I'm going to take this one. I'm going to take it all the way down there and take it all the way up there. And that is the center line of that vertical web. So then I'm going to match this to that. And maybe I shouldn't have done that right away, but now I'm going to do an offset and I'm going to make it 2 inches. And now I'm going to come this way and that way. And that's the vertical web. Now I'm going to match this line. I want to impose its properties on that and that. And now I'm going to say, I'm going to fill it. And I'm going to go from there to there. And I'll zoom in here and I'll fill it again. And I'll go from there to there. And for the moment, I think I'm going to get rid of some of these. Just those were construction lines. But now I want to focus on this truss. Now, typically, the way we're going to do this is we might miter this on the corner, but typically that's not the way we're going to do it. So what we might do is we might extend this line out to there, and then we're going to trim that right there, and we'll do the same thing up here. And then we'll extend that top chord. So the top chord is running all the way to the outside. And right now, I'm not going to worry about these right here, but they'll have to be detailed in some way where they go to the outside wall. And you'll see why I'm going to put off doing that after I go through a few other things here. So now I'm going to say this is 100 feet long. And now I want to measure the effective depth. So I'm going to do dim lin, dimension lin, linear. And I'll go out there and it's 6 feet, 5 1/4. So I'd like to know what the proportions of this truss are to make sure I'm within the ballpark of all those guidelines that we talked about. And for parallel chord trusses, we said that the depth to span ratio can be anywhere from L over 24, or excuse me, 1 over 24. So the depth can be L over 24 up to maybe L over 12. It can actually be more than L over 12, but normally that's not practical because the web members start getting really long and they are inclined to buckle. So, but I want to know, am I in the right proportions here? So I'm going to take the 100-foot long dimension, and this right here is about 77 and a quarter inches. So I'd divide 1,200 by 77, and I'm going to go do that. I just always like to keep an Excel open. I'm going to say this is equal to 1,200 divided by 77, and I'm getting close to 16. Now, I would say 16 is a really nice, it's a fairly deep truss, but that's good because we've got glass up in this truss. And if the truss deflects too much, the glass might crack. So I like the fact that this is fairly deep and fairly stiff proportions. So what I'm going to propose is the following. We make our bays about square, and a way to do that is to say, well, let's just divide 100 feet, um, which is 1,200, divided by 16, and that comes out to 75 inches. So we're going to make the spacing on the vertical web members 75 inches. It's a nice clean number. So I'm going to take this and I'm going to say copy. And now I'm going to trim because I don't want to break my bottom cords or my top cords. And I don't have the whole truss there, but you get the gist of it. I'm going to now say the following. So this is 8 bays, and then I can take all of this and do it symmetrically. So I think if I sweep in this direction, I'm going to mirror that around this line. Nope. Well, boy, I think I'm getting tired. Okay. Now we have a rule when we do trusses that we would like all the members intersecting at a given point to have their centroids going through a single point. And we call that the working point. So I'm going to show on this drawing what the working point is. there's a working point, and there's a working point. And that's the center line of the web. And now I'm going to do an offset of 2. And I get that and that. And now again, I'm going to do some trim here. So I'm going to take that and that and this and this. And I'm going to say trim. And now I can get rid of all that. And I'm going to match the properties from there to there. And we would take all of this and we can copy that from right there to right there. And I'm not going to draw these in right now. So, given where we took that section before, we won't see these members where they're obscured by the decking and the insulation, but we will see them underneath here. Let me go see this section here. So we're going to see the bottoms of these trusses, and then we're going to see, excuse me, those web members, and we're going to see every portion of the web member above that point right there. Okay, so this is the new truss, and I don't know what I did right here. That was weird. And I'm going to do the following. This will get me to the halfway point. And then I'm going to take this one and I'm going to mirror that right there. Okay, so we will now copy this along. Okay, so I'm going to just check some things here. That's 2 feet 9 1/4 inches. I hope I did that right. Oh, there's something wrong. Hmm. Well, that's not good. I'm almost certain I offset that by 33.33. Okay, well, I might have to make some major corrections here. It's midnight. I'm getting a little tired. So I'm going to let it go at that. I'm going to develop this, and some of you, while you're working on this, maybe you'll figure out what I did wrong. That's a simple offset function, though. Let me try something here. One more time. I'm going to do an offset of 33.33 inches. And I was supposed to go from there up to there. Whoa, okay. So that's exactly what I wanted it to do. So here's the problem. I said the dimension of this. Let me do this. 2 feet 9 1/4. Oh, of course, it's correct. Because if I take 0.78, this is fractional inch fractional feet. 0.78 times 12. And I got to put an equal sign in front of that. Okay, it's 9 1/4. I think I'll have to check what fractions of an inch I've got the AutoCAD file set to. This is not 9 1/4 exactly. So if I said, well, it's the closest thing, closest quarter of an inch, then this would be 9.25. Okay, so I hope that that helps. I know that some of you may not be very facile with CAD, but this will get you started. And I may go through at some point and do another little extension of this video where I draw these sections and put in all the square tubes. But that drawing will be simpler than this one because the parts will be simpler. And also, I suggest in your CAD file that you draw those over here because a lot of the dimensions on this thing you're going to pull off of here. And I would have drawn it this way, except that at some point I was trying to give this drawing a shape that would be suitable for a PowerPoint presentation, and it doesn't work too well if I put another big long thing out here. Um, but that's a easier way to draw it. One of the things I love about CAD is you can draw it out here, and then if later on you want to, you just move it over somewhere else. When we used to work on drawing boards, you didn't have that luxury. Okay, I'm going to bed. If any of you have questions after you've looked at this, uh, let me know.